Welcome back to Codex. Our speaker today is Anna Little from the University of Utah. Professor Little is an expert in mathematical data science. Today she'll tell us about constructing features from data. Take it away, Anna.
All right. Thank you very much, Dustin, and thanks very much to the organizers for the invitation. Very excited to be here today and tell you a little bit about my research. Now it did that thing where it didn't want to let me advance, even though we checked it, but it is now. Okay, so today I'm going to be talking about making features from data and kind of a few different aspects to this. As we all know, we're living in an era where data is really exploding. I think it's something like the amount of global data in the world doubling about every 4 years. So really, really steep increase. And so I asked AI to make me a picture of exploding data, and this is what it came up with, which I enjoyed some of the aspects of. But our goal kind of in all this mess of information is to try to create the best features that we can. Okay, so there are a few different considerations here. So what do we want when we construct features from data? One of the most important things that we want to do is dimension reduction. We want to go from a very large, unmanageable number of features to a small number of meaningful features. If possible, we would like for these features to also be interpretable, to lead to some kind of scientific insight, which would help us make decisions or policies that are relevant in the real world. And then another thing that we often want to do when we're making features from data is to make them invariant to certain nuisance sources of variation in the data. And then, if possible, we would like to understand what we were doing. So we would like to have some kind of theoretical analysis supporting the algorithms, so we have an idea of when things might go wrong. Okay, so I kind of opted for a bit of a high-level talk, telling you a little bit about a lot of different topics I've been working on. So hopefully that'll keep it from getting too boring. But I want to start off talking about dimension reduction, so one of those first goals. So here, it's a very simple setup. We have data points x1 through xn living in some potentially very large ambient dimensional space, RD. And the goal is to embed data into a low dimensional space where we can better visualize it, do downstream things like clustering it, etc. Okay, so this seems like a very reasonable goal, but it's actually a difficult one to achieve. So why is dimension reduction so hard? There are a lot of things that make this really challenging. So we're trying to squeeze data into a very small number of dimensions. And in this process, we want to preserve both the local and the global geometry of the data. But it's often hard to do both of those things at the same time. If clusters are present, we would like to reduce the cluster variance. So we sort of have competing goals when we're doing this. So just to kind of illustrate the point, here's a cell mix benchmarking data set published back in 2019 in Nature. And so this data set consists of 5 different cell types. And first here you see the PCA plot, which, things are kind of fuzzy. The different cell types are kind of blurred and overlapping here, for these 3. But from the biological perspective, the PCA plot gives a better global picture of what's going on, because these 3 cell types are really much more biologically related than the purple and the green. On the other hand, more modern dimension reduction algorithms like UMAP and t-SNE, UMAP being super popular in the biological world these days, they do a much better job separating the different cell types. So you can really see very good separation between the cell types. But what is lost is often the global structure, that the global structure you saw in the PCA plot kind of gets all moved around. Okay, so So most of these dimension reduction algorithms utilize a loss function or a matrix, which is constructed from Euclidean distance. And we'll see this, this sometimes works, but there are a lot of contexts where this is not really a useful full metric. For example, you could think about if I had data points sampled from this snake, and I look at the Euclidean distance between a point on the head and a point in the middle of the body, that's very small. But in terms of the geometry of the snake, it would be very long. So Euclidean distance wouldn't really capture the right underlying geometry in that context. So an alternative construction is, so one metric I've spent a bit of time using and analyzing is a path distance. So this is a data-driven metric where distances are defined relative to some data set that you have. And there's a parameter P controlling definition. And so basically, it's if you want to think about the distance between two data points, xi and xj, you can search for the best path through your data, connecting the points. So it's the minimum over all paths connecting the data points. And then you can measure the length of the path by summing up all the individual edge lengths to the pth power. That's like the pth norm of the vector of edge weights. Okay, so this may look a little weird at first. So what's kind of the intuitive idea of what's happening here? Well, this parameter P actually has a really big impact on what best path through the data you should take and what the corresponding distance is. So if you choose that parameter small, close to 1, then the density of the underlying data has little impact and best paths are short. So this is like the figure here on the left, where you're going to take a pretty direct path to go from the left side of the moon to the right side of the moon. On the other hand, as you crank up this parameter, the way you're measuring the length of the path, it's really zeroing in on what the longest edge is. And so it's going to really take a path through a high density region of the data. So that will be more important. You're going to take like a longer path through a high density region. And the choice of this parameter balances these two considerations. Okay, so the density of the underlying data is clearly having an impact here. And this can actually be made very precise by thinking about, well, what is happening in the limit as the number of data points goes to infinity. In particular, we can think about some underlying geometric structure, which we'll model as a manifold, as a d-dimensional manifold, and assume that we have data sampled according to some density function rho. Then with an appropriate renormalization, you can show this discrete path distance converges to the following continuum limit, where the distance between x and y is computed by taking the infimum over all paths along the manifold connecting the points. And then the distance of that path is measured in the following way. This little absolute value of gamma prime would be how just your little arc length element, measuring the length of the path, but you weight that length according to the density function along the path. Okay, so you can think of this as kind of a density reweighted geodesic distance. Okay, so this is kind of neat because it's encoding the geometry, but adjusting it based off of the density. And so let me tell you about a few different cool things you can do with this metric. So first of all, one thing that you can do is you might want to cluster your data. So for example, you could combine this metric with spectral clustering. So let's assume you now make a weight matrix where you connect data points xi and xj using some kernel function eta, but essentially based off of this power weighted path distance. From those weights, you can construct a graph Laplacian matrix and then use its low frequency eigenvectors to embed the data into a low dimensional space. and cluster the data in that low dimensional space. Okay, so why would you want to do this? What advantage does this give over the standard approach, where here's just a simple illustration? Let's say that you start off with this image of a sort of desert landscape. And if you create features, which are a combination of the pixel information, of the color information, and the spatial information in the image. So for each pixel, you can take a little patch around the pixel with the color information and its spatial location in the image, make a graph Laplacian from that information. If you do this according to Euclidean distance and look at the second eigenvector of the random walk Laplacian, you can see, well, it's going to cut left to right because it's such an elongated domain. Whereas if you look at this same eigenvector with a graph Laplacian constructed from this path metric with a P of 2.5, you can see it's really that this cut is following the horizon and really respecting the underlying geometry of the image. Okay, so that's kind of the motivation. In addition to that discrete distance having a nice continuum limit, you can also think about what happens in the context of spectral clustering when you make this discrete Laplacian matrix. Does it converge to some limiting operator as the number of data points goes to infinity? And it turns out that it does, and you can write this down explicitly. This limiting operator for the graph Laplacian, is a combination of Laplace-Beltrami operator with a drift that's essentially pushing you in the direction of the gradient of the density. This may remind you of things, if some of you have seen diffusion maps and what they do in that paper is a similar kind of decomposition. What's a little bit different here is that everything is multiplied by a power of the density. So in this context, this operator generates a diffusion, which is really accelerated in regions of high density. So then there's many ways that you might quantify what does it mean to converge to this operator. But one of our recent papers, we established spectral convergence for the low frequency eigenvalues and eigenvectors. So essentially proving that if you take a bandwidth, h, just a little bit larger than n to the -1/3d, then the relative error of the low frequency eigenvalues and also the error of the eigenvector approximation that you get, it converges to the underlying true continuum ones at a rate close to n to the -1/3d. Okay, so to sort of put this in context a little bit, there is a really vast and continuing to grow literature on spectral convergence of graph Laplacians. So there's lots of results and different approaches for this. And the rate that you get in the standard setting of Euclidean distance is a little better than what we get. But the key difference here is that our metric is random. So, not just this graph construction and the sampling of the data points, but the metric itself is random. And so to control its behavior with high probability requires a little bit of a bigger bandwidth, leading to a slower convergence rate than in some of the other papers in the literature. Okay. Okay, so that's one kind of cool thing that you can do with those distances. Another application, well, okay, maybe a criticism might be that you worked hard to compute all of your pairwise path distances, and they encoded actually a lot of global information about the global structure of your data. But then you fed them into a local kernel, maybe if you used an exponential kernel in the construction of your graph Laplacian. And so somehow you lost a lot of information in that process. So in some contexts, you may want to hold on to that global information. And so an alternative approach would be compute those same distances, but embed those distances with an algorithm that does better at preserving global structure, something like classical multi-dimensional scaling. So what is classical multi-dimensional scaling, or CMDS? This is a very popular algorithm for embedding data into a low-dimensional space, and essentially finds the best low-dimensional coordinates y that it can to preserve, as well as possible, the inner products of the high-dimensional space in the low-dimensional space. Okay, so I should point out that when P is 1, this is not a new idea. This is an algorithm that's been around for a long time, known as isomap. However, it does seem to be really useful in a lot of data contexts to change this underlying parameter to a different value of P. So let me just illustrate this in a little picture. So coming back to this cell mix benchmarking data set that I showed you in the beginning of the talk. So we saw, okay, the PCA plot preserving the global geometry, the UMAP and the t-SNE plots having much better separation of the cell types, but losing the global structure. And now in this second plot, I'm showing you what happens when you compute these path metrics with a P of 2, and then look at the MDS embedding of those distances. And what you see is pretty neat, and that you see the same global structure as the PCA plot, just pretty much up to a small rotation. But it sort of denoised it in the sense of having much better separation between the cell types. Okay. And then one last application that I'll mention of these data-driven path distances is multi-manifold clustering. So what I've been talking about so far, when we consider paths of edges, we're thinking about consecutive edges in a path sharing a common node, right? So this would be, okay, classic path. You have this little sequence of edges that come together in a node. But alternatively, you could consider paths of triangles where consecutive triangles share a common edge, right? So now instead of a path of edges, we have a path of triangles that share an edge at the link. And you could really keep going into higher and higher dimensional spaces, right? You could have a little path of pyramids that share a triangle. And in general, you could consider paths of d-simplices where consecutive d-simplices in a path share a common face. Okay, so why is this a useful thing to do? Well, this kind of metric can be really useful for solving something known as the multi-manifold clustering problem. So in this context, you have data points which are sampled from a collection of manifolds, say M1 through MK. And the goal is to partition the individual data points according to their manifold label, right? So we might have, data points from all 5 of these rings, and we want to partition them into the individual rings. This causes these intersections of the manifolds, though, cause a lot of problems for traditional clustering algorithms. And so most of the standard algorithms would not succeed in this context. So our goal here is, can we construct a distance which can differentiate the individual manifold components? Okay, so the kind of key feature that we would like to leverage in doing this multi-manifold clustering is the fact that these manifolds will intersect at a sharp angle, and somehow we want to pick up on that angle. So to kind of illustrate the idea, just think about, very simple case where you have 2 intersecting planes. And let's say these planes are two-dimensional and you consider paths of triangles constructed from your data points. Well, in this case, you're going to be able, if you have, any two data points on the blue manifold, you can always find a flat path of triangles connecting them where there's no sharp angle changes along the way. On the other hand, if you have one point from the blue manifold and one point from the red manifold, any path of triangles that you construct from your data points at some point along the way is going to have to take somewhat of a sharp turn. Okay, so this is kind of the intuition that we want to leverage in constructing essentially an angle-based path distance. So what we're going to do is we're going to create, we have our data set, we're going to create a set of local simplices. This is assuming knowledge of the intrinsic dimension of the data. So that's something that you do need to know, but given that, you make a set of local simplices, and then you create a graph on the set of simplices by, by weighting to adjacent simplices according to the angle at which they connect. Okay, and so if they connect with a completely flat connection, theta is close to pi, this weight is close to 0. And then we're going to compute an infinity path distance in this simplex graph. So it's the same metric that I showed you in the beginning, but we're taking p to infinity, and we're really measuring the length of any path as the worst angle encountered along the path. Okay, so
Anna,
yes.
Can you go back to that slide with the angle? So should I think of like an affine subspace containing V1, V2, and V3 versus V1 prime, V2, and V3 and hunt for a principal angle to get theta?
Yeah, so what's going to happen, like in a higher dimensional space, is that this shared face is always going to be d-1 dimensional. And so you can just pick some, maybe take the centroid, pick some base point, and now if you go out to this, apex node, it's just a vector, right? It's just a vector from that centroid, and so you can just compute those two vectors and explicitly compute the angle in between them, if that makes sense. So it's going to be orthogonal to that shared face.
Thank you so much.
Yeah. Any other questions? Okay. Right, so you can analyze this. You can get some high probability theoretical guarantees here. For simplicity, what we've done so far has been and this is work in progress, which I really hope will be on the archive in the next month. But we first just assume that these are affine spaces to keep the analysis a little bit simpler because it's already a little bit complicated. But if you have, say, manifolds which intersect, linear manifolds which intersect at an angle theta, and tau is the noise level, so you assume you have observations from these manifolds plus noise. A really critical parameter here is the scale at which you do this computation. So think of E here as being the typical edge length of these simplices. And so you need to choose it kind of in just the right size. You need to choose it bigger than the noise level so that sort of on a manifold, these simplices will be roughly parallel to the underlying manifold. And then you also have some, density constraints that come in to ensure your between manifold distance stays large. But anyway, the punchline is that when these conditions are satisfied, you can prove that with high probability, this metric will differentiate the two manifolds. Certainly, when you have, your manifolds curving around, you're also going to get an upper bound on the E, meaning you can't take it too large or if things are curving too quickly. Okay, so one of the key advantages of this approach, I would say, is that it is quasi-linear in the sample size, because you can essentially approximating infinity path distances is cheap, can essentially be reduced down to computing connected components in a graph. So it's very scalable in sample size. Most other methods are at least quadratic in n. There is a caveat, though. The dependence on the intrinsic dimension is bad. So things do, kind of blow up as this little d increases up to about, d of 5. I would say this does pretty well. Beyond that, you probably want to use a different algorithm, but for very low intrinsic dimension, it works very well. Okay, so just to kind of summarize this first part of the talk, some of the advantages of this data-driven path metric are that it provides a flexible framework for balancing density versus geometry when encoding similarity. It's useful for dimension reduction and clustering, simultaneously reducing the cluster variance and preserving the global geometry. And there's kind of an underlying, rich mathematical framework for analysis, which is really nice. But there are some disadvantages. So it can be sensitive to noise because you're computing things from a single best path through the data. That's more the case as you take p large than p small, but that's certainly a consideration. And then another criticism, which is a very common criticism of many modern data science methods, is that the derived features are not interpretable in terms of the features that we started with. And this is actually really important in a lot of applications. So there are definitely certain contexts where people really feel like they need to understand exactly what the features are and how decisions are being made. And so an alternative, which is an idea that has been around for a long time, but still I think still a relevant one, is instead of doing something quite so fancy, is to just try to learn the best linear metric that you can, but where it's very, very clear how the distances are being computed from the original features. However, ideally, we would still like to do this in a data-driven way. We would still like to leverage data that we have to learn the best linear metric that we can. So, so you can think about the setting where you're given pairs of data points. So let's say you have some xi, yi, and then you're given label information along with those data points that says these points are close or these points are far. So you have a bunch of pairs of points labeled close or far, and then the goal is to learn a positive definite or positive semi-definite matrix M such that dm is predictive of these labels. Okay, so this is trying to learn what's known as the Mahalanobis distance between the points, where that Mahalanobis distance is kind of computed like a regular Euclidean distance, but it's scaled by n. Okay, you could alternatively phrase this goal as we want to learn the best linear map that we can, such that when we apply this linear map to our data points, the Euclidean distance in that embedded space is predictive of the label information. Okay, and so these goals are related by the relationship that, in this case, M would equal AA transpose, because if you look at the Euclidean distance between these embedded points using A transpose, you'll just get the Mahalanobis distance where M is equal to AA transpose. Okay, so here's the kind of picture illustrating the idea. At some point, I'll make this look better. This was done on my iPad and I need to improve it. But the idea is that we start off with a bunch of points. We have pairs, some are close, some are far. We're trying to find the best linear transformation that we can where, right, the far points are going to get elongated and the close points are going to get pulled closer together. Okay, so we came up with a probabilistic model for this where, okay, we assumed that we have labels from pairs of points, but the labels are generated with noise. So without noise, you would have some ground truth M star driving your distances, driving your relevant distances, and you would compare that with a threshold tau star. And if it's large, they're far. If it's small, they're close. But now we assume the actual labels that we observe are corrupted by noise, so we get some mix-up in our labeling procedure. But from the noisy data, we want to estimate, these underlying parameters m and tau. So it turns out you can actually write down what the maximum likelihood estimators of these parameters would be, and they minimize the following empirical loss function, where you do have a dependence here on the noise distribution. The speed noise is the CDF of the noise. And so in practice, yes, you're probably not going to know that in practice. However, there's sort of a convenient choice here, which is if you in practice choose this phi noise to be a sigmoid function, then the result will be that this loss function is convex in the parameters that you want to learn, which is really nice because you can then just solve it with a straightforward optimization. And if your noise doesn't really have that noise distribution, solving this optimization, this convex optimization problem with the misspecified noise still in practice appears to give you a very good solution to the original problem. Okay, so then in a recent paper, we analyzed the sample complexity required for this, and essentially you can show that if you have a sample size scaling like the dimension squared over epsilon squared, then if you use these parameters estimated by minimizing that loss function for your prediction, you get a nearly optimal cost up to order epsilon. And you can also show that if the underlying true M has a low rank structure and you apply a spectral truncation to your estimation for the M, then it's still achieves a nearly optimal cost. So this is nice because many results can't guarantee this explicitly, that the process of spectral truncation is not going to mess you up even when you do have a low rank structure to your M. And then you can also show that, in fact, the estimated M hat is close to the estimated M star, but it's a much more restrictive sampling condition, and I don't think that that's sharp, so I have not put it here. But just to say that can be done if you're trying to get the parameters close. With enough data, that can be done. Okay, so a couple of publications related to this first part of the talk on dimension reduction. So a recent paper, JMLR paper on the path distances with spectral clustering, a paper on combining with MDS for the analysis of biological data, and then very short conference paper for the MMC stuff, and then a JMLR paper for the linear distance metric learning. Okay, maybe this is a good time so I want to tell you a little bit about invariance for feature construction, but maybe before that, should I pause for questions? Anybody have any questions at this point?
You mentioned earlier computing the entire matrix of all of those path distances. Is it an expensive operation, or do we have a fast algorithm for this?
Yes, great question. So I went fast and I didn't discuss that. So it certainly depends a bit on if that graph is sparse or dense. But if you do it in a sparse graph, then let's say you have like order n edges in the graph, like you would in a K&N graph. If you wanted to explicitly compute all of the pairwise distances between all your points, then that would be quadratic, which is not great, right? That would be order n squared to do all of them exactly. But there's a couple caveats here, okay? So that full computation would be order n squared. However, you can compute, if you just care about nearest neighbors, you can do that quickly, and you can compute that in linear complexity. If you want to do P of infinity, there are tricks to let you do that in linear complexity. And then there are also like low rank approaches that you can, essentially use a set of landmarks, compute things exactly for the landmarks, and then extend to the bigger matrix. And so sort of Nystrom-based approaches to kind of do a scalable approximation. So I would say there are good ways around it, but if you wanted to do the full exact computational problem, it would in general be quadratic.
Thanks.
Mm-hmm. Yeah. Any other questions? Okay. Okay. So in the last part of the talk, I wanted to shift gears a little bit and talk about another goal when making features from data. And this is that a lot of times you want to remove nuisance sources of variation in your observed data. So this, I guess the work that I have done related to this has been inspired by applications like cryo-electron microscopy, where you get a bunch of images of molecular structures, but what you see coming out of your microscope is incredibly noisy. And within each noisy image, you have a molecular structure that can be translated all around. It can be appearing in any spot. It can be rotated. And then you have this sort of projection from 3D to 2D. Okay, so this is an extremely challenging application for many reasons. So first of all, the low signal to noise ratio, things look very noisy. There are these random rigid motions, like these translations and rotations of the underlying molecular structure, which confuse your observations. And then you also have, random deformations of the molecule, or you also have non-rigid motions as well. For example, you can think about this molecular structure here on the right. This tail often kind of flips around, so it doesn't always stay in a static configuration. So all of these make this a very challenging application. So the basic setup of interest in this context is that you have a large number of very noisy observations of a target image or signal, and your goal is to recover a high resolution approximation of that target signal. And noise here can mean many things. It can mean additive noise, or some like underlying group action that's acting on your points, translation, rotation, rescaling, etc. So in this context, it's often helpful to utilize certain group invariant features, but of course, the more invariants you force into your data, then the less descriptive it can become. So there's a bit of a balancing act here. As I mentioned, the full cryo-EM problem is really, really challenging. So one thing that people have done is to start on something less overwhelming. So one of the most basic toy models that is inspired by these kind of applications and has some of the complexities that they have, but not all of them, is the 1D multi-reference alignment model. So in this simplified model, what you assume is that you have some hidden signal F that you're trying to learn, And you can't observe it directly, though. You observe it subject to some random translation plus a bunch of additive noise. But you get access to a lot of samples of it. So we'll think of capital M here being the sample size, and that's going to be pretty big. From all of this noisy data, you want to recover the underlying hidden signal F. Okay, and sigma squared here will be the variance of, we'll think of epsilon I as being a white noise process, and it'll be the variance of that white noise process. So the bigger the sigma, the harder it is to see the signal in any individual observation. Okay, so there's various approaches for solving classic MRA in the literature: synchronization, where you first try to align the signals; method of moments, where you try to cover it from their relevant statistics. The one that I want to focus on today is the method of invariance. And this is where you try to recover the hidden signal from translation invariant features or Fourier invariance. The basic idea being that you take all of your signals, you map into the Fourier domain, and then in the Fourier domain, you construct features by careful construction, which are translation invariant. People also do EM algorithms, which tend to work well, but be a little bit expensive to run. But let me kind of focus here on the Fourier invariant approach. So it's based off a very simple observation that if you have F, which is just a translation of Y, then in the Fourier domain, that translation only affects the phase, doesn't affect, the magnitude of the signal. And so you can construct Fourier features which cancel out these phase factors. The most basic one is the power spectrum, where you just take the magnitude squared. The next most complicated thing that you can do becomes a function of two frequencies and is known as the bispectrum, where you combine the Fourier transforms together in this specific way, which cancels out all of those phase factors. Okay, so unlike the power spectrum, the bispectrum is invertible under pretty general conditions. And so there's been a lot of focus in the literature on using the bispectrum for recovering the hidden signal, and what's the sample size required, et cetera. Okay, so this has been a focus in the literature, but most of the work considers random rigid motions. And one interesting thing to think about is, what if these motions are not rigid, like inspired by the molecule where the tail flops around? What if you have non-rigid motions or more general diffeomorphisms? And here, this is very hard in general. I don't think there's like an approach that can handle all cases of that. But the simplest thing you could think about as a first step is to think about the case of linear diffeomorphisms. So where you have translations plus dilations. Even the simple case is pretty interesting and challenging. Okay, so an alternative model then is to add in dilations into this classic MRA model. So we have hidden signal. It's now going to be randomly translated along some axis, randomly dilated with some dilation factor, the variance of that dilation distribution being eta squared, and then still corrupted by additive noise. Okay, so here's a little, and then from all of that noisy data, you're trying to recover the hidden signal. Here is underlying, well, here's an illustration of the model in 2 dimensions, where from all of these noisy images of a cat at various amounts of zoom, we're trying to, and the cat could be, shifted around, we're trying to recover a high resolution image. Okay, so I think I'm going a little bit slower than I anticipated. How long do you guys usually go? Like 50 minutes? Give me a time cutoff.
Let's go 50 to 55 minutes. So
Okay.
You have 2 to 7 minutes.
2 to 7 minutes. So I'm going to so sorry, I probably went too slow in the beginning. So I'm going to kind of speed it up here at the end. but I'll summarize it for you. The dilations essentially smear out your Fourier invariance, but with knowledge of the dilation distribution, you can develop an unbiasing procedure which recovers the bispectrum of your hidden signal. And you can prove this and sort of quantify the error of learning the power spectrum and the bispectrum of the hidden signal. So this relates the sample size, the additive noise variance, and the dilation variance. And these rates you can compare with the classic ones in the literature for classic MRA. And so because you can estimate the bispectrum with high accuracy, and the bispectrum uniquely determines the signal, the story seems simple, and that now all you have to do is invert the bispectrum. This is just a little picture illustrating the unbiasing procedure, but I'm going to skip over that. And you have many algorithms for that, for inverting the bispectrum. So it seems like, okay, problem solved, but I want to end by pointing out why it's still actually not quite solved, why it's still a lot of challenges to think about in this area. And one of them is that, unlike the power spectrum, the bispectrum, the sort of more descriptive translation invariant feature, does not preserve the norm of the signal. And this actually has a big impact when you think about higher and higher frequency signals. For the power spectrum, as you increase the underlying frequency of the hidden signal, things stay stable. But it turns out the error when using the bispectrum grows exponentially, just because the norm of the bispectrum is not preserved and tends to get smaller and smaller for high frequency signals. So that, I think, is certainly a real challenge for real data. And then another challenge is that theoretical guarantees for inversion of continuous bispectra aren't really present in the literature. So I swept that under the rug a little bit, but most of the MRA models and the theoretical guarantees treat the hidden signal as a discrete vector. And in the more maybe natural model of thinking about it as a function, don't have theoretical guarantees for the recovery yet, except if that function is band limited, where things kind of go back to the discrete case. There are some really interesting results along those lines here. Okay, so here's just some figures illustrating that even when you can really accurately learn the bispectrum, the inversion is still quite challenging in practice. Okay, so just to wrap up, this is a generalization of the MRA model where we think about the effects of translation, dilation, as well as additive noise. We're inspired by this idea of trying to capture non-rigid motions in the data. And future directions include theoretical guarantees for sort of full theoretical guarantees for continuous models. Certainly learning the dilation distribution is needed for doing these things in practice as well. So that's also an interesting question for future research. But in the interest of time, I'm going to call it a day there. A couple of references on the MRA papers. The last one probably being the most relevant to what I talked about today. And thanks to all my collaborators and students who have contributed to these projects. And thanks again to the audience for listening and the organizers for the invitation. And I'll open it up for any additional questions.
All right, thank you. Before questions, we'll express our appreciation by clicking buttons. Questions for the speaker? Let me stop the recording.